Okay, let's have a look together quickly at the solution. And if you have questions, now is a good time to ask them so I can address them here. So after we've loaded the weather data set, the first step is to calculate the solar position for the entire year of 2022 with the 10-minute time resolution. And you do this by providing the time vector to the get solar position function. And this will calculate the solar zenith and solar azimuth. Then to calculate the plane of array irradiance, the simplest is to use the pvlib function. Of course, we could use the equations, but that will take a little bit more work. So we use the get total irradiance functions, and then we have the two surfaces, the two roofs, and for each of them we give the array tilt, the azimuth, the solar zenith will be the same, the solar azimuth will be the same, and then the weather components we provided for the 2022 data set, and the type of surface is the same, and model isotropic in this case is we use it the same way. So we calculate this one. Then we get these, basically these two data sets. Where is my that looks something like this. And the data set will, of course, contain the global as well as the components that are calculated using the same functions. Now, another prompt here was, so we've calculated basically, this is the plane of array irradiance with the 10 minutes resolution. And then in the exercise, it said how much insolation. So first calculate the plane of array irradiance for the two roof surfaces. We did that. After which calculate how much insolation each roof surface receives each month of 2022. So insolation is different than irradiance. So the irradiance, you can think of irradiance as power. How much power does at any point in time is incident on the surface, whereas insolation is energy. How much energy did that surface receive in this period of time? So whereas irradiance is measured in watts per meter squared, insolation is measured in watt hours per meter squared or kilowatt hours per meter squared. Now, in order to transform from power to energy, we need to know what is the period we calculate the energy for. So we calculate it for 1 hour, and our measurements are every 10 minutes. So we need to integrate the 10 minutes over 1 hour to get the energy from there. So transforming from power measurements every 10 minutes to kilowatt hours. So from watts to kilowatts, we need to divide by 1000. And to go from power every 10 minutes to hourly energy, then we need to divide by 6. And that's how we transform from irradiance to insolation. If you have a different sampling time, it will be a different factor that you go from irradiance to insolation. So now we have a vector of insolation for every 10 minutes. What's the kilowatt hours there? And then we need to, let me run this one. And then if we just say this one here. So we would have here POA. Okay, this is maybe not the best because it's in the middle of the night. But this will tell you every 10 minutes how many kilowatt hours have you basically received in those 10 minutes. Then we'll need to add it up for each month of the year. And one way to do that in Python is with the resampling method and summing up for each month. So all the measurements from February we sum up, because energy is a cumulative variable, so we need to sum it up to get the total energy received in that month. So we sum up for each month all the energy received in that respective month, and we calculate the insolation, the monthly insolation. So we'll get, instead of here, I don't know how many values we have, probably around 50,000 values. The size of the array will shrink that to 12 values for each of the roofs. And then we put this into the data frame so we can plot it nicely. And then when we do this, we get something like this, where we get each month of the year, and then we get here should say insolation, not irradiance, insolation. And then, for example, in January 2022, we get about 180 kilowatt hours per meter square. So that's how much energy was basically shining on that surface. Whereas we have less during summertime. And then you can also see how well the two roof surfaces, so which one collects more energy during each season. And then, of course, you can, if you want to optimize the orientation of your PV array for a certain month, then using a model like this can be useful. But then you can see here each orientation, how much energy it receives, and we can clearly see that the north-oriented receives more, which is according to what we also expect. Then we also want to see, okay, how much do we receive in an entire year? So then we just sum up the insolation variables for the entire year. And then we get, for the Northeast, we get 2,000 kilowatt hours per meter squared, whereas the Southeast, we get 1,900. So there's not a significant difference. There's like a 0.5% difference. But you can take this one and then compare it with other locations. For example, in Denmark, we get about half of this for our optimal orientation. And then as a small exercise, I wanted you guys to see, or because we didn't have plane of array sensors to validate, to kind of compare with something else, at least to see that if you are getting the same ballparks. And for that, I recommended to use the PVGIS. And then if you go to PVGIS, to the PVGIS tool, you need to provide it a latitude and longitude, and you take that from the exercise parameters. You say go, you say go, and then it will take you to the map of Saint Pierre. And then here you have a number of tools, and the ones that you want to use for this exercise is grid connected. And this tool has a transposition model inside. It allows you to select a weather database. We'll use the default one. And it allows you to set the slope and the azimuth. Now there's a bit of a difference in the way that pvlib considers south and the way the PVGIS considers south. So in PVGIS, south is 0 degrees, east is -90, and west is 90. Whereas in pvlib, south is 180 degrees. And then you'll see kind of this difference if you use different PV software. So you just need to transform the azimuth from the pvlib convention to the PVGIS convention. And then if you crunch the numbers on that one, you'll see that for the tilt is the same, but the azimuth in PVGIS for the Northeast will be -166. And then for the Southeast is gonna be 14 degrees. just because they use different conventions of what is the degree for south. So let's punch that one in. So it's gonna be, the slope is still gonna be 9, and then this is gonna be the northeast roof, and we press visualize results. And then we get, if we press here radiation, we can get the monthly in-plane radiation. And then if we look on this side, we can also see the yearly in-plane radiation in kilowatt hours per meter squared. And also this is kilowatt hours per meter squared. So it's kind of is the same type of unit. So here for the northeast, we get 2041 kilowatt hours per meter squared. And here we got, for this one, 2060. So it's very close. If we look at the other one, that is going to be 14 degrees. So the south-oriented one, we get 1850 per year, and we get 1900. So a difference of 50 kilowatt hours. Now, the difference is mainly because PVGIS uses TMY dataset. So it uses a typical meteorological year, which has been derived from 16 years of measurements from 2000 to 2016 or something like that, or 2004 to 2020 for the SARA 2. Whereas here we use data from 2022. So there is a bit of difference in the input weather data set because we don't have the same weather data set. Okay, so that was exercise 1. If you have any questions for this one, otherwise I have some questions for you, as in we have a small quiz. Let me see. And let me start it. I'll start with quiz 1. So we will I'll copy and paste this into in the chat. So now you have another link in the chat. So please go there. And I have a few questions for you. So first question, what sensor do we use to measure the global horizontal irradiance? So if you remember the white sensors in the weather station or in this tracker. Okay. Do we have other opinions? Okay. Okay, so we use a pyranometer, a thermopile pyranometer. That's the name of it. What sensors do we use to measure plane of array irradiance? This is a bit more complicated. Okay, so the correct answer, we use both. We can use either a pyranometer or a reference cell for plane of array. We use reference cells because they are cheaper. We also use reference cells because they have the same shape and the same spectral response as the panels. We use pyranometers because they are more accurate for global irradiance. However, we do not use reference cells, so we can use pyranometers both in the plane and for horizontal, but we do not use reference cells for horizontal because they do not see the holes, or they start to have reflection losses when the sun is very low. So solar cells are less accurate for global horizontal irradiance. They are ideal for plane of array because they have the same shape, the same flat shape as the panel. So that when panels see reflection, reference cells see reflection. Whereas pyranometers have this dome shape and they have no reflection, basically, no reflection losses, because they receive light due to the dome shape. They receive light uniformly from all shapes. So both of them are useful for plane of array, only pyranometers for the horizontal one. What is the name of the energy equivalent of solar irradiance on a surface? So if solar irradiance is power, how do we measure solar energy on a surface? Yeah, most of you got it. It is insolation. So very good. Let's see the last. Okay. Okay. So what is the typical azimuth or cardinal orientations for system located in the southern hemisphere to get, let's say, the maximum irradiation during the year? How do you orient the panels? You orient them south, north, east, or west to get the maximum installation during the year. This is more for a general system, not for the NR system. So in the below the equator, in the southern hemisphere, the typical or the optimal orientation of the panel is north. Now let's use PVGIS for a bit. And PVGIS has an interesting feature. So once you specify a latitude and longitude, you can use PVGIS to find the optimal tilt or the optimal tilt and azimuth. So what is the optimal tilt for a north-oriented PV array on the TerraSand campus? So you put the optimal orientation to be north. Remember, north is 180 or minus 180 according to the to the convention here, because south is 0, north is 180 degrees of that. So what is the optimal tilt of the panels according to PVGIS? So once you'll see the optimal tilt here written. So once you select optimize, let's say for a south-oriented system, if I run it and I optimize, it tells me that the optimal tilt for south is 0 degrees. So what would it be for north? I put here 180 with optimized slope. 22 degrees, so not 9, it's 22. Okay. It also depends a little bit on which data set you use. So you might, in some instances, get slightly different different values. So 22, 24, they're both around the same one. So let's see the last questions, which I want you to, it's a bit of a tricky one. Use PVGIS to determine what is the optimal azimuth for a PV array located in the TerraSand campus, according to PVGIS. So do you think it's 180 or it's something different, and why is it different? So if we click on optimize slope and azimuth and run it, we get 24 and 151, minus 151. So that is somewhere northeast. Is not completely north. Why would that be? Now there's two kind of answers to this. The most relevant answer here is, why is it not? Because it should be north. It should be 180. It is because you have mountains around, and you have something called horizon shading, which is also shown here. So once you have relief that's blocking some parts of the sun, the optimal orientation may no longer be the geographical, or like what you would normally just calculate based on geographical location. You also have the mounts blocking, so you might get slightly more irradiance if you oriented in away from the mountains. And this is what you can see here. The other explanation, or in addition to that, you also, the way that PVGIS calculates the optimal orientation is based on data. So it takes this TMY data set, runs it for all the possible tilts and azimuths, and calculates the numerical maximum, basically, of the insolation. And then you get an angle, a tilt, and an azimuth that gives you the maximum insolation based on data. But then if you have a different data set, you might get something different. So let's try with a different data set. So for a different data set, which is made from other years, it's slightly different. So it's not 151, it's 163. So it's still because you have the mountains there, but also there's a bit of variation between the data. So you kind of have these two competing factors that give you a slightly different optimal insulation. But the differences, so in this case, you would get 2200 watts per meter squared, and if we then orient this one north, then the difference is not that big. So it's a few tens of kilowatts per meter squared. So it's not that significant.